Hi engineering students. I'm coming to you from my office and I'm going to try some new recording software because my one that I was using keeps crashing on me and it's very frustrating. So this one has a nice little webcam built into it. So I don't know if this is going to be annoying, terrible, an improvement, we'll see. But we'll try it out. Now on the screen in front of you, you'll see that we have a little picture of Mrs. Smelly with her brand new cart that I built for her over this Christmas break. I think I've told you about this, but I don't think I've actually shown you a picture of it. Maybe you've seen it around campus. She is coming and going all the time. And I just want to bring this up to you again because, firstly, there's some similarities here with things that we're about to be doing. I've intentionally kept this particular project, Mrs. Smelly's one, just to myself. I didn't involve you guys. I just want to jump in and do it, get some practice. But you'll see down the bottom we have some caster wheels. Those are big 4-inch off-road wheels, so she can go outdoors. But what just arrived an hour or less ago is some little caster wheels for Mrs. Jones' cart. I got 4 of those. For this one, you can't really see it spinning. Maybe you can. I got little compact ones, and there's a very good reason for that. It's actually going to help with the design. These ones are locking. You stand on that, and it locks from spinning. Simply presses onto the wheel, and then it keeps going. They also sent me in the same bag a little orange screwdriver to put it all together. So great, I have an extra screwdriver now. So I got 4 of those. What else do we get? Some Christmas presents here. This is the actuator for Gil Addison's computer desk. Okay, so this is the thing, once we run power to that, and I have the bits and pieces here as well, this is going to extend out. And right now, the length between the 2 pins is about 200 millimeters, which is about 8 inches, and that's going to travel out another 4 inches. That's the stroke. This has a stroke of 4 inches. Correct? Yes, it does. 100 millimeters. And that's what's going to drive that thing up and down. So if things are coming in, I'm going to be road testing this pretty soon. I think that's kind of fun. It's fun to spend other people's money, actually. It's always fun. All right. And one last thing, too, I want to point out to here with Mrs. Smelly's cart. I just want to make the reminder here that I was able to do this for someone who needed it because I had a particular set of skills and experience. And because I had those, I could show love and compassion to someone in a very unique sort of way. So Mrs. Smelly had bruises on her arm from pushing around her old metal cart. It was very hard to push it through the dirt and through the turf and things like that. It was noisy, it was rattly, it wasn't big enough. So I made all those changes. And I could do that because I know how to use fractions and I know how to use Pythagorean triangles and things like that. And that is how I designed this cart and built it. And I can use tools and things like that. So all those things intersect to let you fulfill the love of Christ to other people in really great ways. So don't ever forget that. That's why we're doing this. That's why we work with PathPoint, with Mrs. Jones. And there's another secret project coming up soon with Mr. Mitchell. So keep an eye out for that in this semester. Okay, let's get into the truss work. Again, let's see how this new screencaster behaves. I hope it's going to work well. All right. I should be able to go all the way over here, actually. There we go. Okay, so here is a little truss bridge for you. And I would love it if you would get out your little kit and if you would actually put this one together. This has a lot of similarities to the other trusses that I've had you do, but it also has a lot of, I shouldn't say a lot, it has some critical differences, which is why I'm highlighting it in this second video in week 19. So first of all, this is a 45-degree truss. Okay, this is our classic little geometry symbols to show that all these angles are identical. Okay, 45 degrees everywhere you look. And remember, that is how this kit is designed, to be able to create 45-degree triangles. It also creates 60, 60, 60 triangles if you get 3 members of the same length. All right, so far things are feeling pretty normal, but let's do our typical things. Let's apply a nice healthy 1,000 Newton load. Let's put some simple supports on both ends. Okay, this is like across a valley or a river or something. And I think your instincts are wanting you to also fill in these little side loads, these reaction supports. And those are going to be 500 newtons each. No surprises there. This is what we call a symmetrical truss. And as I said to the 9th graders earlier this week, when I talk about a symmetrical truss or a symmetric truss, I'm actually talking about 2 things. I'm talking about the structure, and I'm also talking about the load. Both the structure and the load have to be symmetric in order for you to call that a symmetric situation. You can have a symmetric structure, but if the load is off center or imbalanced in some way, then you don't get the simple, equal supports on both sides. So that is an important thing which I haven't really mentioned yet, both structure and load. All right, we're going to go into this and we're going to start to create the free body diagrams. The one thing I need to do is I am going to label the joints. Sorry, let me try to make it a little less flourishy. I don't know why that was doing that. There you go. And because of that wonderful symmetry, which really helps us out, I'm going to do something else too. I haven't done this before, but I am going to label the joints in a symmetric fashion as well, showing that really there's only like 5 unique joints that could be analyzed. You don't need to do the ones on the right if you've done the left. So I'm going to give them the same labels just to help drive that concept home. Okay, let's do a free body diagram. Let's give ourselves some room here. Let's put this over here. Here we go. Let's do a free body diagram of joint A. Now there's really only 2 places you could start to analyze this thing. You got to start somewhere. You can either start from the extremities, joint A. You could start from, conceivably, I should say, you could start from joint C because there's that 1,000 Newton load. But can you imagine trying to sit down and do an FBD of joint C? Just kind of fast forward 2 minutes into the future of you trying to do that. Look into the future. Look at yourself doing that. Hey, self, how's it going over there? Uh-oh, your self has some problems because you have 3 forces pulling up. And then you got these 2 forces pulling sideways. Now, even if you take out the symmetric ones, you still have a label here. You still have member BC, member CE, and member CD. Okay, that's even not including the other symmetric side of it. You have 3 unique members needing to be solved and only one, and one force, but you only have 2 force equations to try to solve those 3. You can't solve 3 unknowns with 2 force equations. That is why we are not starting at joint C, we're doing at joint A. Okay, I think you should sketch in your forces coming from those members, and this would be the correct way to show those. I hope you're getting a sense already of whether they are up, down, left, right, which way they point. Let's start by doing a vertical foursome. Don't mind that noise in the background. Someone is sanitizing a classroom. Vertically speaking, we have the 500 newtons, and then we also have the force of AE times sine of 45. The sine of 45 creates the vertical component of that force rather than the full force itself. Okay. And if we play around with this a little bit, then we do that. I just added FAE sine 45 to both sides. And then I will divide 500 by sine 45. And what we get there, I'll do it on the next line. I like to have it nice and cleanly written. If you tap that out on a calculator, you're going to get a force of 707 newtons. All right. 500 divided by sine 45. And then we'll go ahead and we'll do the horizontal foursome. And we have force AB, all of it, because it's perfectly horizontal. And then we have the force from, what is that, force AE cosine 45. Okay. Now again, this is giving the horizontal component of force AE. By the way, the cool thing about 45, 45, 90 triangles is that sine of 45 is exactly the same value as cosine of 45. Both of them are equal to root 2 over 2. If you're in probably pre-calc, you've learned that, or you're about to. In calculus, you should definitely know that, 11th to 12th graders. This is approximately equal to 0.707 and then some change, which is, you know, like, in other words, about 71%. That's a great way to think of it too, that when you multiply something by cosine or sine of 45, it's 71% of the whole thing. Great way to think about it. But my point was that sine and cosine of 45 both give the same results because both legs of a 45, 45, 90 triangle are the same length. That's why that is true. So if you get it wrong, it doesn't matter. You'll get the correct result. Only in this case, 45, 45, 90 triangles. Okay, we will add FAE cosine 45 to both sides. Voila. Now, if you have kept the value of FAE on the screen, don't retype in 707, but use what is on your calculator screen still and just multiply by cosine 45. You're really just undoing what you did right here. Okay, you divided by it first, now you're kind of multiplying by it. Remember I said it's the same value. So what you will find is that you get back to exactly 500 newtons again. All right, so that horizontal member, FAB, this one right here, that is exactly 500, same as the support reaction right next to it. Good, good. We're getting there. We got 2 out of the 7 unique members. We're talking 1, 2, 3, 4, 5, 6, 7. We have 2 of them. And quickly tell us, are these in tension or compression? Let's see how you do. I'm testing you right now. I'm quizzing you. Little self-quiz. Is member AE, this one, is this in tension or compression? Tick, tick, tick. It is in compression because it is pushing on joint A. That's what that force means. It's pushing on joint A, and when things push on other things, you saw in the video the other day from my shed, that is meaning the thing itself is also in compression. Okay, when something is used to push on something, it itself gets compressed. So that is a compression member. This one is a tension member. It is pulling to the right on joint A. All right, let's keep on going through. We're going to launch next into a free body diagram of joints B. All right. Now this time we are going to start with the horizontal foursome. Let's just glance up at that again. Actually, I can probably keep that on my screen. Sorry. my pencil, my electronic pencil here gets in the way when I try to scroll. Okay, what do we have over here? Actually, I guess we should mark those in. We know that this force is going this way because that's the other side of member AB, also pulling on joint B. We must have a force going this way from member BC, and then we must have a force going this way. That is member BE. So let's do the horizontal sum. We have force B, or let's say AB. I tend to do things in alphabetical order, if I can remember. FAB is going to the left. We have the force of BC going to the right. That's why it's positive. And we already know what FAB is. It's right there. It's the 500. So really what that tells us, it's very simple. You can spot it without all these words that I'm using. That is also 500 newtons. Look at that. So in this case, what we're seeing is like a consistent force going along that bottom rail of 500 newtons, which is just an interesting pattern which emerged. And we'd probably expect, if this bridge pattern was repeated longer and longer with more and more triangles making this up, I think that'd just continue the whole way along. Usually the pattern is, is fairly predictable. Okay, let's go into the vertical sum. And by the way, this is where my video crashed last time for the second time. So I'm on new ground here. It's exciting. What do we have there? We have right there on joint B is where we're looking. What are our vertical forces? We have one. There's one. There are no applied loads on this joint. The 1,000 newtons, the 500 newtons, they are not anywhere to be seen as far as this joint is concerned. We only have that upwards one, and that is member BE. Look, just to prove it, BE right there. So this is what we're writing in black. We're writing FBE. Now, we do have another side of the equation. We have that 0 right there. The sum of the forces in the vertical direction is 0. We know that. That's a fact which lets us do everything that we're doing. That's critical. And it is equal to force BE. So what do we make of that? What does that mean? Well, I'll tell you what it means. It means that force BE is 0. That's it. That's the whole revelation. We have something kind of special here. This is called, BE, is called a zero force member. Okay, a zero force member. That's weird. And by the way, if you want to read about this, this is on page 256 to 258. And it's kind of a weird thing. You have a member inside your truss, which according to your calculations, carries 0 force. At which point you ask yourself, why is it there? Why do you have something in the truss which is not carrying any load? Well, that is a good question. Maybe we'll get back to that. Okay, so what do we do with that? Do we kind of wipe it out? Well, it's definitely neither tension nor compression, so we're not going to list anything. Over here, you know what, let me try to just clean up a little bit and try to erase that green. I'm making a mess, aren't I? Getting rid of stuff that I shouldn't be. Well, actually, no, let's get rid of that guy, because turns out there is no force in that member, so I'm actually quite happy to leave him out of it. Okay, so that's tension, we know that. That's just nothing. In fact, maybe I'll even write like 0 just to remind us. We haven't forgotten about it, it's just nothing. We could travel along, let's do the free body diagram for joint E. And yes, I'm doing these over and over again. Oops, I'm so sorry. Because if I've learned anything, it is that we definitely just need more practice. I know I came on pretty strong last week, So we're trying to remedy that. Okay, here are some other unknown forces right here, and then right here. It's a little bit wobbly, but you get the idea. You know what, I'm going to redo that. There we go. Okay, let's do the free body diagram. Remember we know what force of AE is. BE was 0, so we only have 2 unknowns and 2 equations. That's the golden situation. It might be a good idea, by the way, for you to pause the video right now, do this yourself, and then pick it up again and see if you got it correct. That could be a good idea. Just saying. All right, I'll do the vertical foursome. We had, I've got to remember what was up there. Force AE at an angle of 45 degrees. Again, doesn't matter if it's sine or cosine. I just picked one actually. That one was positive because on this joint it is upwards and to the right. And then we have, remember, CE, which is downwards and to the right. So I'm going to make that negative because it is downwards and to the right. Now again, what this tells me, if I just look at this, let's just look at this logically. Maybe I'll make it even easier. I'll subtract this and put it over this one side. FCE sine 45 equals FAE sine 45. Now you just look at that logically. Look at what I've just created there in that equation. Forget like the workings of doing the math. Just look at that logically and see what that is saying. It's saying that FCE equals FAE. If you want to say that we divided both sides by sine of 45, you can say that. That's true. But the point here is that those are one and the same, and so we have the result right there. FCE is 707 newtons. Very good. We will then do the horizontal foursome, and we had a component of force AE, and it was positive because it was to the right. We have the component of force CE, also positive because it's also to the right. And then we had force DE was pushing to the left, and that is the only left thing here out of the three. That is the only thing pulling to the left, so it's actually really important. FDE, it's negative because it is counteracting that. Wait a minute, my thing is in reverse. There we go. Oh man, this is a mirror image camera. That's confusing. Now we know what FAE is, we know what FCE is, and I actually remember that when we multiplied those by cosine of 45, we actually got back to 500. Do you remember that? That already happened. So I'm actually just going to write in 500 for both of those. They were both 707. 707 times cosine of 45. It brought us back to the original 500. So what this is telling us is FDE is the granddaddy of all. It's 1,000 newtons. Oh, so we're getting more force. FDE is 1,000 newtons, right up in there. And is it in tension or compression? It is in compression. Okay, force CE is in tension because it is pulling down. And look, I guess I could do like the joint analysis of joint D or joint C, but I actually don't need to. I've now got 1, 2, 3, 4, 5, 6 of my 7 unique members. And look at joint D. Don't go to joint C. Joint C's got so much going on. You don't want any of that. Stay out of that mess. Look at joint D. It's got the exact same situation that was happening at joint B. it's got this horizontal situation, and then a member kind of sprouting out the side, and it's because that perfect horizontalist with the member coming out that that member coming out the side can't possibly have any force associated with it. It's actually the same. It's the same as this picture right here. Okay. Again, you have the word they use is collinear. Okay, that's really hard to do on this backwards camera. That collinear structure with something, oh boy, sprouting out the side of it. Okay, it doesn't matter if it's coming out at a perfect perpendicular angle or some kind of oblique angle. Doesn't matter. It's the point is that it's coming out of two collinear members, so it can't do anything all by itself. There's nothing to react against it. Newton's third law, action and reaction can't come into effect. So that tells me, just the logic of it all, the way we saw it behave earlier, that member CD is also a zero force member. It just is. All of those three vertical members are zero force members. Okay, so we've solved the whole thing. Okay, that is the whole truss. Now, the usual question I want to ask at the end of any truss analysis is, which member should we be keeping our eye on? Which one is in the most danger? Which one are we worried about? And looking through our results, we would say we're most worried about DE. It's 1,000 newtons. If any of these members are likely to go down and break, in tension or compression, it's probably going to be the one loaded the most highly. Force DE. So we put it in red to remind ourselves. It's it's this one here. This is the potential problem one. That's the one that we should use to calculate, what kind of steel or aluminium or wood and how thick is it going to be and what kind of cross section are we going to give to it. Is it going to be like a solid square piece of something? Is it going to be like an I-beam? Is it going to be like a hollow tube? The point is you would use that member to make those decisions, and then you guarantee that around the rest of the truss it's going to be able to survive all those other loads as well, because you're arguing, this is called arguing from the greater to the lesser. If the greater one can handle it, all the lesser ones can handle it as well. All right. Now, again, back to these ideas of these zero force members. If you have a truss that has members with zero force in them, then why are they even there? What purpose could they possibly be serving? I'm going to try to explain this. It may not be easy, but we'll see what I can do with the level of knowledge that we have available to us. So, wait a minute, sorry, messing up already. Okay, so we had, I'm intentionally drawing this a little scrappy just so you can see the different members. Okay. And then you have, okay, so that's our truss. So what if we took out those three zero force members? They're not doing anything, right? There's zero force. They're just there for a free ride. So what if we did 1, 2, 3, and we got rid of them? Wouldn't this thing be behaving just the same? I don't know. Would it? Think about that. Remember, we still have all of these pin joints at all of those locations. How are they labeled? So I'll make sure I get this right. A, B, C, D. Okay. A, B, C, D, E. And then through symmetry, we just gave those the same names. Actually, let me remind myself as well of which ones were in tension, which ones were in compression. We had compression, and those three were tension. Okay. Let's put a C for compression. These are all in tension. Excellent. Okay. So think about this. We're pulling down. In fact, oh, you have a physical truss in front of you because you built it, right? You built it when I said to build it because you're good at following directions. So you can actually take out those zero force members on your own truss, and then you load it in the way that we looked at. You know, you pull down on it and you have it resting maybe on a couple of books or something, flat on your table. What is going to happen? Well, I'll tell you what's going to happen. This area here is in tension. So I just got to get out my own kit now. I got to show you. I have a bad feeling like you're just sitting there watching someone play video games in another window, and I'm just talking to myself. I don't know why that would be. Don't do it. Okay, if I have two things like this and I pull on them in tension, the whole thing is kind of acting like one great big rope. Okay, one great big cable. If it were loose or sagging with all that tension, it would actually snap into place. It'll stay really quite nice and straight. It's like having the joint there doesn't really do anything. Actually, we could have taken out joint B, as it turns out, entirely. We could have made that one big solid plank all by itself. You know, member AC, and the whole thing would behave just the same. It's all in tension. You wouldn't see any difference whatsoever. So the zero force member that was right here actually isn't doing a whole lot. Okay? Mathematically, we already saw it's not doing anything. Practically, in real life, it's actually not doing a great deal. If anything, it might be sort of helping with the natural weight of this thing, as it tends to, like, you know, under gravity's influence, under the, you know, the cars and trucks and trains driving along this. Of course, it's going to sag a little bit. So if anything, member BE is doing a little bit of work to kind of act like a suspension cable. Okay? Not in the analysis we did, mind you, but in the analysis we did, we didn't take into account the fact that there could be a load at joint B. See, we didn't put one there. But don't you think there would be some load at joint B? Don't you think that these things all weigh something? Don't you think that there's, you know, like a roadway surface that has load everywhere across the whole thing? So, you know, if we had put those in, then joint B would actually, member BE would actually start to do some work. So that's one reason for those zero force members, is that in real life, there's more load than what you actually put in. Life doesn't come at you in point loads. We've already said this before. Life doesn't come at this bridge with one big load down in the middle at joint C. There's a little bit of load everywhere. So that member, which is currently a zero force member, it wouldn't be once we bring in more real life load. So that's one reason why it is there. The other reason, oops, yeah, that's fine. Let's now think about this part of the truss, okay, spanning from E to E. I got my same sticks. Here they are. What is this experiencing? We said it was 1,000 newtons. Okay, that's fine. We know that much. But is it tension or compression? It's not tension. It is compression. And look what's happened. You can already see it's already trying to do it. As you compress on a jointed pin like that, it just kind of pops, just snaps out sideways. I'll do that again in case it happened too fast. Look at that. It just pops out and falls apart. Which, by the way, makes the whole thing crash and fall into the river, and everybody dies. It's terrible. So in this case, in that area, joint CD, it is a zero force member in theory. Yes, in theory. But the kind of theory we're doing doesn't account for that popping out. It just doesn't have the power to handle that dynamic situation. We're doing a very simple static analysis where we balance forces and things stay put. I guess it's true that if this thing did stay absolutely laser sharp lined up and there was no vibration or moving, there was no imperfection in the machining or or the holes or anything, nothing off center, then maybe you could keep pushing on that and the forces would be laser sharp lined up and they would perfectly push against each other and maybe it wouldn't pop out. But we know that in real life it does. There are imperfections. There are imbalances. There are vibrations, and the slightest one will make that go boink. So the zero force member in this case, so glad I made these kits. I love them. The zero force member in this case is anchored down there to point C. So as these members experience that compression and the desire to pop either upwards or downwards, that zero force member kicks in as a stabilizing structure. Okay? It'll act in tension if it wants to keep the thing from popping upwards. It'll act in compression if the thing tries to pop downwards. Whatever you do, it's there, it's got you covered. It's going to make a nice rigid triangle. So that is the other reason for apparently zero force members. They are firstly there because in real life there's more load than what you plan for. Okay, so they kick in when that happens. And the second reason is that they guard against instability. Okay, when the truss tries to pop out, it guards against instability. Now, you could sort of take this a little further too. With my kit here, you could say, well, why don't we just not put those joints there? Wow. I'm having a really hard time pressing these things in. Oh, okay, I'm confusing myself. You say, why don't we just get rid of those joints? Maybe I shouldn't build this in front of you. Maybe I don't have enough time to do that. What if you just looked at the larger triangle of the whole arrangement? You having fun? You having fun watching me build something off screen while nothing happens? Good. You know, they say that people's patience levels really taken a hit during this whole pandemic. I wonder what you're experiencing right now. Oh, I did it. Okay. So, like, why don't we just substitute it with this? Like, why do we need a joint, you know, here at D or here at B and B? Why not just make them big, long, solid members without joints? Then they can't pop up or down. We just have back to rigid triangles. And it's like, well, yes, you can, but then if you put a member across there, like even a long, rigid member, it can still pop out. It can still become unstable if there's too much load. If there's too much compression on this top rail, it will eventually just, you know, go like, you know, bend and bend and bend, and then it suddenly go, you can see it starting to go, I'm helping it out clearly. But you know, like think of a big flexible metal ruler, you squeeze it in and it bows out suddenly. So that happens in real life on large scale. And so putting a member that is anchored across to something else at that halfway point, I could be wrong here, I'm going from memory, but I think it makes it 4 times stronger. Pretty sure I'm right there. 4 times stronger in that buckling, collapsing failure mode than it would have been. Okay, so the zero force member makes it 4 times stronger if you put it there, right there in the middle. And that's huge. 4 times stronger. You know what that means? That means you can make the structure, make the member 4 times thinner. It's 4 times less expensive, and it'll be able to do the exact same thing just because you put that little zero force member there to help steady that. All right, well, that is our lesson for today. It's a little bit of a shorter one. I know I beat you up last week, and then we're getting a little easier this week. I promised you that, and I wanted to make good on that. I'm glad to see the toys have come in. We'll start building this. I've got Zach McNeese on a special assignment to start to make some of Mrs. Jones' stuff. And I am going to start working on Gil Addison's pretty soon. I went to the hardware store. I bought a huge sheet of expensive, smooth, high-quality plywood, and I'm going to start doing that very soon. I'm anxious to see how that actuator powers up. Not anxious. Excited? I have anticipation. I'm excited. But that's it. Next week, I think we'll start our second topic of statics in action, and that is something called beams. Okay, beams. A beam is different than a truss, very different, and we'll see how that is next week. All right, have a good weekend. Let me know if you need help with the assignment still. You got up until the end of this Friday to hand it in. All right, see you later.